Buenas tardes.
Good afternoon. Good afternoon and welcome to the Ramón Areces Foundation. On its behalf, I'd like to thank all of you for attending this event. My name is Manuel Aguilar. I'm a member of the Foundation's Scientific Board and a member of the Royal Academy of Science. My specialty is high-energy experimental physics or particle or elementary particle physics. I am currently an emeritus research at the Ciemat. As many of you will know, the Ramón Areces Foundation has had a long-standing support for activities connected to science and technology. The Areces Foundation carries out these activities through partnerships with other institutions and organizations with similar interests, including the Spanish Royal Academies, the Spanish Royal Society of Physics, Royal Society of Chemistry, Royal Society of Mathematics, universities and research centers, as well as other foundations, both national and international. Today's scientific session is a good example of these partnerships. It's the result of a partnership between the Areces Foundation and the Royal Academies of Science and Engineering. The Areces Foundation would like to thank everyone who's participated in the organization of this event, and most particularly Professor Jiménez Sendín and Professors Alfonso Valencia, José M. Gutiérrez Llorente, Petros Koumoutsakos, Carlos Delgado Méndez, and Juan Lerma Gómez for agreeing to be our guest speakers today. And before I give the floor to the co-coordinator and moderator, Javier Fernández Sendín, I'd like to mention something which is an obvious fact, but also indisputable: the growing importance and impact of artificial intelligence. And every AI system are based on algorithms, which are simply constructions based on sets of mathematical rules which make up instructions that can be understood by a computer or a server, telling them how to execute a task. It's undeniable that in the 21st century, we have seen mathematics rise to the front lines of scientific research, as described by Benjamin Nabatut Anton in the book Años, is interesting, although only partly, because mathematics, he said, are an unlimited, invisible world which is not bound by any version of reality. The universe of mathematics is something that will not fit into the human mind. So that's what Mr. Slavatut said, and he continued saying, mathematics are the way I approach the mysteries that other people might approach through religion, mysticism, shamanism. It's the realm of the invisible. Mathematics are something that we can only use through the exercise of our minds. So in that sense, it's something very mysterious because its practical effects surround us all. And so I'm going to give the floor to Professor Jiménez Sendín now, who will be moderating this session. I'd also like to thank all the very prestigious speakers for accepting our invitation. I would like to wish you all a very interesting and fruitful session on a very current topic. Thank you.
Bueno, muchas gracias, Manuel.
Well, thank you very much, Manuel. I am Professor Jiménez Sendín. It's a pleasure to welcome you all here. I'm going to be moderating this on behalf of the Foundation and the Royal Academies of Science and Engineering. And first I'll describe the agenda for the evening. We'll have 5 speakers. Each of them will speak for just under half an hour. Unfortunately, we will not have time for questions after each talk because we have to leave at 8:30 at the latest. So I will take advantage of this opportunity to remind the speakers to please stick to their allotted time. After the third talk, there will be a short break, just to stretch your legs. And then at the end, we will have another half an hour in which there will be questions and answers from our speakers. As Professor Aguilar pointed out, today's topic has 2 parts. A part on artificial intelligence, and obviously I don't need to say that that's extremely interesting because we all believe that it's something that's going to have a tremendous impact on our lives in the very near future. And then the other part is about scientific discovery. And that's important for 2 reasons. First, because scientific discovery is our investment in the future, and it's always important itself. But then also, from the point of view of the topic today, it's a field where AI has been used for 20 years or more. Scientists have been using AI as a tool for at least that long, and so now is the time to look back and see whether it's been effective or not. And that's basically why we organized this conference or this symposium, to see whether AI has really had an impact on scientific discovery, and therefore we can trust that it will really be a breakthrough in the future. So the question basically is whether it's going to do everything we were already doing, only better, like getting a bigger microscope so you can see the same things you were looking at before, but clearer, or if it's something that's completely disruptive, like the first microscope, which in the 17th century opened a window to a world no one was expecting, no one knew was there. So that's a question which I'd like the speakers to try and answer this evening. So there's 5 speakers, and they're not necessarily specialists in AI. They are advanced users of AI, although some of them have developed some of the technologies behind AI. So we're going to hear about topics like biochemistry, weather, forecasts, complex systems, hardware, and basically that's it. I just have to introduce the first speaker and hope that you will enjoy this evening and that you will all learn something. So our first speaker is Alfonso Valencia. Alfonso Valencia is the IQIA professor in the Barcelona Supercomputing Center, which is the National Supercomputing Center, and he heads the Life Sciences Department. He's a biochemist, and apart from being at the BSc, he's the director of the National IT Institute, coordinating Spanish data in the Personalized Medicine Initiative. He works in computational biology, and particularly its application to medical problems. And so on that topic, he has made significant discoveries, including protein co-evolution, which I hope he will explain, the disease network, and more recently, digital twins for cell models, which I think is partly the topic of his talk today. He's part of several international consortia, some or several to do with cancer research, and he was the founder of the Spanish Bioinformatics Network and chairman of the Bioinformatics International Society. And as a result of that, he's also chief editor of the Bioinformatics publication, which is the top publication in that field. Alfonso, you have the floor. Good evening. First of all, I'd like to thank the organizers for inviting me to speak here. It's a great pleasure and a great honor. And I'm going to open this very interesting symposium on AI and scientific discovery. I actually picked this title, The Limits of Computation in Biology, which sounds a bit mysterious, but actually talk about this evening is not so much about those limits, which, if I summarize them, are actually pretty simple. First, advances in biology and therefore computation of biology requires enough computational power, so I'll talk about that, to have enough data, and I'll talk a bit about where we are with regards to data in biology. And maybe I'll be giving you a bit of a pessimistic view. I hope you'll forgive me. I'll speak about models, to what extent we can model some areas of biology, to what extent we have computational models that really reproduce specific areas of biology and what we can do with them. And obviously, I'll talk about how AI is impacting all of these things, benefiting from computational power, data, models, and where it is taking us at this very interesting point in scientific research. And ultimately, the question underlying all of this is, can biology be computed? That is, can we use the knowledge we have, the computational power and the data and so on, and really reprogram in a computer life, biology? I know this sounds like science fiction, and I think that it still is, but maybe not for very long. I'm from the Barcelona Supercomputing Center, so obviously I have to speak about computation power. And we have this supercomputer, Mare Nostrum 5, which is the most powerful in Spain, one of the 3 largest in Europe, with this petaflop peak performance and huge storage capacity. We're also a research institute, which is not always so obvious, with over 1,200 scientists and engineers, with 4 scientific departments. Mine is the life sciences department, as you've heard in the introduction. And what's a supercomputer? Well, a supercomputer is a massive computer which can compute as if it were a single computer with a lot of parallel computation power. And in our case, it's divided into 2 main partitions. One of classic computation with CPUs and accelerated computation, GPUs, with, well, as you know, NVIDIA is one of the largest companies in the world, and right now very much in the headlines. And so that's the next-gen partition with which we can do AI. It's the type of supercomputer that you use to run AI models with various characteristics. It's a very unique facility, and you're more than welcome to visit. Combining these 2 partitions and enabling us to do things which in the public sector are only possible in Europe in the Barcelona Supercomputing Center. And it's a national and a European infrastructure. So we're part of this European network of supercomputing with larger institutes in Italy and Finland, a new one which will start operating in Germany this year, even larger. And that means that European researchers will apply with their projects, and those approved by an external committee will get computation time on these computers. But we're also a Spanish network where other centers will get computation time for national projects. So that's technology at the service of research in Europe and Spain. And we have enough computational capacity for AI. I do believe that. We do have enough capacity to do interesting things. If we compare it with the kinds of resources private companies have, if we think about the $500 billion that we've seen in the headlines in the papers the last few days, probably our capabilities are very modest in comparison. But what we're striving for in Europe and what will define Europe's capabilities in this field of AI will be our ability to activate the computational resources we have to the benefit of European societies and research. And so one of our limitations is computational power, and in principle we have enough computational power. Our second issue with research in biology is about data, and we will see how other speakers in the other lectures will talk about how they deal with data issues in their various fields. But in biology, data, as you can see in the slide, are heterogeneous, noisy, complex, and are interrelated. So any small site, a hospital, will generate huge quantities of data, and the data will be very heterogeneous. It could be imaging data, it could be genome data, and they're very difficult to interoperate because of their structure and their syntactic and semantic meanings being very different in different places, and they're intrinsically noisy. When we sequence a tumor, when we're sequencing normal cells, tumor cells, cells of the immune system, and so the sample is always going to be heterogeneous by definition. And so we're always dealing with heterogeneous data with significant noise levels, with incomplete data, and we have to analyze them in context. It's useless to analyze a genome if we don't know what the patient's condition is, what drugs they are receiving, and what their status is. So we need to look at all of that together. And to make it even more difficult, these are highly private data, and so having access to them is very time-consuming because they are intrinsically private. And somehow, at this point, in spite of having great quantities of data, any hospitals generating huge volumes of really interesting data, but we're finding it very difficult to access that data, to use it for research. I won't go into everything in this slide, which is very complex, but in Europe right now, together with the countries, they decide that the data that are being generated for primary treatments of the patients should be usable for scientific research. This is the European data space, which has come into force, was approved by the European Parliament, and needs to grow in the coming years, and that's precisely what that is about. Data for research, data that are being generated for primary care should be usable also for research. This is the European data space, and there are various projects, I won't go into all of them, as well as national projects that are beginning to deploy the technology to make this possible, to make it possible for the data that are generated in different sites, so that researchers can use data from different sites in different countries within the right legal framework. What's the aim of the European data space? Well, it's about data access through cross-border data access in Europe using AI applications that will be trained with distributed data without removing them from the respective countries. So it will be like a federal system, and private and public institutions will be able to work together, and it will be crucial for innovation in biomedicine. And so there's various questions. Will we be able to mobilize all of this before 2029? Will we have enough funding to do it? Enough of budget? Will we be able to navigate regulatory complexities in order to make this kind of research possible? And will we be able to compete with AI with the US and China by accessing all this data? These are all good questions. And in the next slide, I have a very pessimistic view on how much needs to be done in the next 4 or 5 years for any of this to be possible. And this is an experiment. It's a European health data space. They put out a call for pilot projects, and we were one of the European infrastructures who applied. We asked 3 other countries, Belgium, Denmark, and Norway, do you have genomics data that we can use for this type of analysis to show that this is possible. And all 3 countries, the authorities said, yes, we do have data and we'll do it. And so in summary, 2 years later, after launching this project with the firm support of these countries, Denmark has not yet replied with any data, which is unusual for them. And they haven't been able to fix it in 2 years. In Belgium, they said yes, but the data belong to different institutions, and until we compile them, we can't provide them, and that's taken 2 years so far. And Norway, which sounded so enthusiastic, have told us we have informed consent for the data to be used in research, but we're not certain that it's for the kind of research you want to do, which is a bit frustrating, because how can a patient who agreed some years ago to have his data available for research? And the European infrastructure has said, yes, we have the data and you can use it, but the Access Committee is still arguing, and that's taken 2 years. And so we thought we were going to be shut down, because that the European authority who had awarded the project to us would say, well, 2 years and you haven't done anything, we're going to shut you down. But actually, no, we're writing the paper and they're happy because it's a key demonstration of European difficulties to access data. And I'm telling you this almost as a joke, but it's actually really serious, because it means European patients are not benefiting from all the available data because there are all of these obstacles and issues, which are legal and administrative problems. We cannot fix medical problems because we can't access the data that these patients authorized for research. So I think it's a serious problem, and over the next 4 years, I hope that we'll be able to overcome them. But let's imagine that we had enough computational power and enough data. What do we do with the data? And I wanted to talk to you about models, which is another frontier of biology we're approaching quickly. And in this context, what we're talking about is digital twins. And in other talks, you'll hear about digital twins of the Earth for climate modeling, for climate change predictions, digital twins of cities, digital twins of processors. But in our case, it's digital twins of the human being. In the BSc, all my other colleagues are working in the other digital twins, and they're saying, Alfonso, aren't you doing digital twins of the human body? And of course, if you know anything about biology or medicine, you will realize that producing a twin of the human body is much more difficult than of a factory, because our knowledge of the human body is a lot more limited than our knowledge of a factory. But anyway, that's the dream, to have a digital twin for Anna. So it's Anna's virtual copy in the computer, and we'll be able to use it to input data, develop a sufficiently good model to predict the course of a disease, the optimal treatments, and make choices. Since we can't do this, we divide Anna into pieces. So we can't have a full model of Anna, but perhaps we could develop models of parts of her system, and that's what we do. We have models of anatomical parts. This is a protein with a potential drug. Well-developed molecular biology and other technologies enable us to know how this protein folds and unfolds and how the drug might operate. And in the other extreme of the scale, we have increasingly precise organ models. This is a heart model where you can reproduce the physics of the heart and its electrodynamics, and you can use it to plan heart surgeries. And we are very interested in these other intermediate models. We're simulating a tumor in this case, and what happens inside a cell, basic building block of a system, what's happening inside it, all the molecular components, what's happening also between the cells, how they're connecting and communicating, the cells in a tumor, the cells of the immune system, or with the environment. When drugs are delivered, how do they enter the cell? And so we've developed software to do this, which is called Physibos, in partnership with other institutions. And this is the biggest goal, modeling, combining it with genomics, because we now have amazing techniques that enable us to sequence individual tumor cells and distinguish different cell types and understand what's happening within each individual cell to have sufficiently precise information about the status of that full cell. So we can use that information in order to investigate cell pathways to see what's happening in each cell, differently in each cell, put it into context of what's happening with the other cells and how it's interacting with them, and start to see
proper data and adequate data. This is the social and economic side. What's the scientific side? Well, this is my claim. The only success that we can prove, and it's cannot be debated, of AI as of today is the prediction of proteins. The rest of things we can say that we've improved, we've got systems, it's interesting, but we can say thanks to AI, we've made progress in an area where we'd been working large scale efforts for a long time, and we got protein models for all proteins, for all genomes on the databases. Now, this is interesting. This is 2020. Nobel Prize, the AlphaFold program, which predicts on the base of the databases the structure of proteins. That year, 2022, the technology changed completely. Instead of a deep neuronal network with data, a language model was used like ChatGPT, and instead of texts, it trains with protein sequences, and it speaks proteins. It's sort of strange, but it's true. We've got ChatGPT, which produces proteins. And this is a complete technological change 2 years later. One of the first systems was published not by Google, but Meta, its competitor. But that very year, there was another technological change, and diffusion models, a completely different technological system, was used from the image world to produce proteins. So in 2 years, 3 technological changes to 3 completely different systems to predict proteins, new proteins. These are proteins that have never been seen in nature, so they're not patented, and they can have new applications and functions. Is this enough? David Baker, Demis Hassabis, and George Church asked the question, what is the next frontier for large language models? Is it biology, a foundation model of transcription across human cell types? So AI is not just in the field of proteins, but in the field of genomics. Based on genomes, can we say what genes are going to express for all tissues? Is biology predictable, therefore? Based on all this, can we predict the development of biology itself? This is the big question that is underlying all these developments. And I'm going to finish with this. So we find that we have computing, we've got data, we've got models, we've got AI models that more or less do the same. This is the proposal of all researchers. Instead of doing cell models, let's learn from the genomic data and have models of the cell that are not going to be mechanistic like they used to be. It's going to be completely different. Maybe what we're doing, we're starting to ask ourselves, how do we combine mechanistic models where I know what's happening and I can say this protein goes here and activates this and this protein, with AI models which have learned the data but don't tell me the why and the wherefore. So the challenge today is how we are going to combine the mechanistics that we need, because we want the scientific explanation of why things happen, why this mutation is in this gene activates this other gene and produces this tumor, with an AI model that is stronger in terms of prediction. And this is going to help us to predict the ability in terms of space and parameters, learn about models and predict better than the physical models themselves. And at the end of the day, how are we going to be able to develop AI models that are like a black box but they don't escape the laws of what we know about. In my case, the pathways of real biological information. Not let these models explore spaces that are useless, but only spaces that are useful to understand biology. And this now becomes the most interesting point of computing biology. I'm going to finish with a slide, completely freaky, so to speak, slide. These are our social science colleagues. They have two language models. One represents a doctor, another represents a patient. You convince one that they're a doctor, giving them the information of how a doctor behaves, and the other a patient with the information about how patients behave. And then they chat. What do you feel? How do you feel like? What's wrong with you? This, that, and the other. This is the state of the art in sociology right now. And this is our model for biology. Instead of having agents that are a doctor and a patient, I've got an agent who's a cell or another type of cell. And I say, you're such and such a cell. I convince it that it's that cell, and then they chat. What happens if the language model, cell language model, speaks to the tumor cell and the immune system cell and how they interact? Maybe they can imbibe all the biology, put it into language models based on the knowledge I have, and let them operate as if they were operating in true life, as if they were agents in true life. It's a bit freaky, but I wanted to show you this because although it's weird, this is new territory. This technology leads us to places we didn't know we could reach ever. 2 years ago, we could not have dreamed that a language model could be used to represent the behavior of a cell. Thank you very much.
Bueno, muchas gracias, Alfonso.
Well, thank you, Alfonso, for a fascinating talk. What I'd like to know is, that interaction between patients and doctors, what happens if the doctor makes a mistake? Does the patient get annoyed? Yes, probably does. It's good to know. Well, thank you very much. Now we're going to the second talk. We're going to start moving into the scale of earthly things. José M. Gutiérrez Llorente is going to talk about the revolution of AI in modeling time and climate, which is another hot topic right now. Professor Gutiérrez is professor at the University of Cantabria, and he works at the Institute of Physics of Cantabria. It's a joint center, the CSIC and the university. He works on regional modeling of climate and data, including social challenges like climate change and AI. I don't know exactly what the challenge is, but he will tell us about it. He's the director of the Climate and Data Science Group and has led many initiatives nationally and internationally about climate, including Climate Platform for Climate Services at the CSIC, and he's collaborated with the FAO and Copernicus, led the World Program on the Climate and AI, and he is also one of the authors of the IFCC report in recent years. When you're ready, José Manuel, the floor is yours.
Bueno,
Well, first of all, I want to thank you for inviting me to this fascinating lecture series. I've prepared a lecture which I've tried to make it simple to try to show what science underlies climate and how AI has invaded this area and what we expect for the future. But I want to make it easy. And climate is a very complex system made up of different components, the atmosphere, oceans, the cryosphere, ice layers that interact between among them, and there's a condensation of water in the atmosphere, drops in the ocean, changes salinity. All those processes have attracted the attention of physicists since the beginning of science, and they've tried to formulate the dynamic, understand how this works with models, starting with very simple models and moving into complex models. And in this adventure of understanding climate, discoveries have been made that were very important in physics. For instance, this man here, Dr. Lawrence, in 1963, he introduced a model, which is this simple model you see there, simple in terms of equations. And in that model, he tried to very simply code the dynamics of the circulation of the atmosphere. It's a toy model, so to speak, but he arrived at a series of conclusions and said that it's a non-linear model that is sensitive to surrounding conditions. And he created the deterministic chaos theory, non-linearity, which had a tremendous impact on physics in the last few decades. That curve at the bottom, that means that if you begin with an initial condition in some place in the system and you evolve, that's the trajectory is the red trajectory. If we start at another point and evolve, after a time there's divergence, and that leads to the blue line. They overlap for some time, but they diverge. This means that there's a limit to predictability beyond, in climate terms, a week or 10 days. The weather is unpredictable because I haven't got enough knowledge of the initial conditions. So these simple models have evolved into much more complex things, and they've moved into a first full model that you see at the bottom. This is a much more complex equation with very few variables that you see at the bottom in blue: position, speed on the x-line and height, movement of particles, pressure, the pressure they're under, the isobar maps we see on the television, what the temperature is, what the density is, and what the humidity is. Based on those basic variables, these models are based on the basic laws of movement, mass, etc., and they model the condition of the atmosphere. But there are a series of elements in the atmosphere, and this is important, that take place at a very small scale, and these equations are no good for modeling that, and that's what we call model physics. For instance, convection and condensation. Those arrows point to phenomena where humidity condensates, and that leads to rain. There are convection, deep convection processes, saturation, series of processes that cannot be simulated. You have to turn them into parameters. What does that mean? You've got to use sources and drains in the equations and do it in such a way that there is no divergence. So it's like the kitchen of models. There's a dynamic side, but then there are the parameters that come under physics, which are the more complex part of models. It's what takes longer. It's done at grid and subgrid level. And at the end of the day, computing regarding all this is very complicated. I've got a model on the right. I want to simulate what happens with the atmosphere in the real world that you see on the left. So I've got to use mathematics. Mathematics, non-linear mathematics, I've got to solve. Numerically, I've got to solve this problem. I've got to divide the globe into little sections, boxes. Imagine each box covers a degree. 360 by 180 boxes, so many in height, depending on the levels of the atmosphere, because the atmosphere is not by two-dimensional, it moves vertically, and the most important problems take place on that level. So I've got millions of parameters associated to a simple instant of this discrete element, which is the atmosphere. And what happens? Well, to do a simulation, I've got to start with an initial starting condition. got to know what the status of that volume, that the atmosphere is right now. And starting there, I can use equations to predict the evolution of the atmosphere. That's what's called the data assimilation process. I won't go into it in detail, but it's very, very complex. If you haven't got a good initial starting point, what happens? Well, as Lawrence said, divergence will happen immediately from the good trajectory, which would be what would you would have if you knew about the conditions perfectly. The nearer you get to the true present condition, the better things will go. And that's the basis of everything. And there are sophisticated mathematical models which, on the basis of the world network, observation network, which has been developed for this purpose, it's one of the first world coordination initiatives that has been particularly successful to share all this weather information, because in contrast with what Professor Valencia said, in weather, data are not always shared optimally. We don't have problems with the data, but information sharing is not always optimal. So on the basis of that information, we use mathematics and we iterate using the numeric methods, and we look at what the atmosphere is going to look like in 1 hour, 2 hours, 3 hours, 3 days, and a prediction, 3-day prediction. And based on this initial condition in 3 days, this is what we're going to have. This is the storm is coming in here, and this, based on this atmospheric condition, we're going to have this rainfall or whatever parameter it is. So everything in weather is based on this, on these models and simulated conditions. Now, this is associated with the previous talk. It's very, very expensive, costly to simulate weather models, because imagine that I got unlimited computing resources, I'd use it all up, because I'd make such a small grid that I couldn't do anything with it. In order to execute a weather model with a 100-kilometer grid, I need this computer. This is a supercomputer, Met Office computer, as Professor Valencia explained before. He spoke about this. This is a bit older, before AI developed, but of the 500 most powerful computers in the world today, 7%, almost 10% of them were devoted to this, what I've just explained, weather simulation models, and that's all they did. And what do these simulations do? Well, there are many different areas. The most well-known prediction is the short-term prediction. I want to predict what's going to happen with the atmosphere in weeks, 1-2 weeks. That's the limit. Professor Lawrence, in his very easy model, established that limit. So I start the model today on the 5th of February, or the 6th of February, and I simulate a few weeks, and I need just a model of the atmosphere. It doesn't have to be more complicated, because all other weather elements at that scale are constant. Now, what is the problem? There are other scales. The seasonal prediction, I start my model today, but I want to know what the next summer's going to be like. Can we know this? Yes, because we use the atmospheric model and apply an ocean model whose timescale is slower. The ocean is slower in its movements, and the prediction ability is greater because of that. So I see the effects of the anomalies in the ocean in terms of up to a level of 1 degree in temperature, and that allows me to predict, or I can even predict decades into the future. And this has a lot to do with climate change and predictability. And then on the other end, I've got to enter all the components of the weather system, chemistry, the carbon cycle, everything to simulate the weather at the end of the century as a result, among other things, of human activity. And this is done with the same machines, the same models at different scales. So all this gives you a huge amount of information that is available, and there are large infrastructures where this information is shared in a federal way, so to speak, and there are petabytes and petabytes of information available. For what? Well, to train AI models, for instance. And This issue of open data has a paradigm that is based on reanalysis. That is what I said before. We got observations of today's weather, we put them in the model, and we got the status of the model, all variables of the model, winds, temperature, humidity, pressure at different heights, 500 MBs, 1000 MBs, that's the surface, and all that volume. I assimilate all the observations every day, and since 1940, 1st of January 1940 to date, there are simulations that are called reanalyses that give me those data, all that information. The European Centre of Medium-Term Prediction, which is the flagship of weather analysis in Europe, it's one of the most it's the most prestigious centre in the world. Its latest reanalysis, Era 5, is available on the web. Copernicus, you can download the data, and it's 700 TBs of information. Now, those 700 terabytes of information, we have 25 kilometers of resolution, 16 variables, 37 levels, since 1940, hour by hour, which is, those simulations are done hour by hour. What happened? Well, this is, well, wonderful for AI. I mean, this is one of the sets of data that are most used, and all AI models in weather prediction are based on this because they're state of the art, and they can allow you to learn about the evolution of the atmosphere hour by hour. And this is where AI comes into play. It didn't develop all of a sudden yesterday. I was talking to my colleague at the Ciemat. He's been working in this area, machine learning, for decades. Machine learning is a discipline that began many, many decades ago. And there was a seminal study in 1986, where one of the many models of machine learning, which are the neuronal networks you see on the right, there are inputs, outputs, neurons at intermediate levels that do simple calculations that mimic the human brain. And there was an article that led to the 1.0 of neuronal networks. That was Hinton and co-workers. They introduced a method to learn those parameters based on data. I got a model with an enormous amount of parameters, and what I want to do is I want to get those parameters to adjust in such a way that when I put an input in, it gives me the output I want. I want my face, well, I want the output to be my face or somebody else. So those are the 1.0 neuronal networks that were already around 40 years ago, and we have used them, I would say, tremendously. It's the most used machine learning model. But in 2015, Hinton, once again, that's why I got the Nobel Prize recently, and other co-workers, they were in the big data era. We're talking about era 5 reanalysis type of things. They developed the 2.0 neuronal networks, or neural networks. And all the technological giants came together because they wanted information, images, information, text information, etc. We got Google, we got Meta, we got NVIDIA, Huawei, all of them lead initiatives in weather because the methodologies that were generated for image recognition are applied in weather directly. So these 1.0 neural networks are 2.0 neural network, deep learning neural networks, and a simple network with few neurons in the hidden layer. We go to a network with a lot of hidden layers, and it's not any longer a simple operation, but it's a complex operation, convolutions, where space and time are considered together recurrently. So we go from having a very simple thing to having a tomahawk surface-to-air device. So what happens? 5 years ago, Google launched a model called GraphCast and began to compete with the other models that are used for weather predictions that we see on the telly. And everybody was taken aback with this because in this first initiative, and then new models were launched, ForecastNet, and that is even more complex, and that can run through periods of years, and it has applications in weather. It can look at climate change and seasonal changes, and then the Pangu weather of Huawei, and then in October 23, yesterday, so to speak, this morning almost, the European Centre published operationally, experimentally, a version of AI. They've got a model called AIFS, which is probably the best short-term prediction model, and they produced a version called AIFS, and experimentally, together with the predictions that they already had. And this is something that nobody could have imagined. It's unbelievable. In the blink of an eye, we're talking about AI that is in operation. It's experimental, but it's running and led by the European Centre. Now, how does all this work? Well, it's easy. All these data that we had since the 1st of January, 2nd of January, 3rd of January 1940, we compare them. From the 1st of January, we go to the 2nd, from the 2nd to the 3rd of January, until we have a whole set of data which is equal to the hours that are included in that period of 60 years. It's an enormous amount of information. Every dot is 1 million data. So we put all that on one of these deep neural networks. We train it to see whether we can predict tomorrow based on today. And it turns out that I've got a whole set of techniques, including convolutional networks that go from the predictors to find the patterns of what we want to predict for tomorrow, or the famous GraphCast, which uses not those weird convolutions but graphs, and it finds for each point or dot, it finds the elements, the links that have to be associated to other points in space to predict what is in that dot, that area, and then using a graph neural network, we can train all that, and it's much more efficient because we can look for what we want in each dot, or we turn it round, and then we go to transformers, a different type of technology which is even more sophisticated. There's something called attention, and every point in space is a potential. This is the technology that the language models use. Every point in space is a potential predictor of some other point over time or in the next period of time. So this gets more and more complicated. But at the end, what we have, I've got an initial condition, which is today, the 5th of February 25, yesterday, and we got a neural model. So what I can do is I start today, I apply the neural model, and I got a prediction for tomorrow, for today, the 6th. And then I use that as an initial condition and obtain a prediction for tomorrow, the day after tomorrow, etc.
And so with that, if I look at rainfall, the forecast that was generated by these AI techniques, like GraphCast and the European Centre, indicate rainfall around here, which will be reaching us, but not today, tomorrow. And according to this, tomorrow in Madrid at 12 noon, it will start raining. And if I compare this with the operational model of the European Centre, which is down here, this is the physical model, which requires a supercomputer like you've seen, and each cycle takes 12 hours to run. The top one with AI takes 1 hour on any computer in a modest research institute. It doesn't have to be the BSc. And if we look at the patterns for today and tomorrow, they're very similar. And if we look at the metrics, and I won't go into details, but if we look at the metrics comparisons, we'll find that the AI model on top, with standard verification parameters that have been used for years amongst meteorologists, put us in a position where the curve at the bottom, the yellow one or the orange one, is a Microsoft model called Aurora, which is a foundational model, is trained on a lot of things, but the next one is AFS. And the red curve is the operational model, which takes 12 hours, the physical model. And there are others at the top, but there's already models that do it better than the prediction models we had up to now. And clearly they've been trained with data emerging from one of those other forecast systems. They've not been trained from scratch. There's a sort of leapfrogging or synergies between physics and AI, because without data for training, there's no AI, and the training data have come from simulations and not really observations. So these are the products of the European Centre, and here with AI, we get to a point where I can explain things. It's not that these are black box models. What we want now is to understand how the neural net is working, because I understand the physics model. I've built it. There's some fundamental. I don't know what the neural model does, but there are these techniques which are called explainable artificial intelligence, or XAI, which, with simple diagnosis, enable us to understand what the neural model is using to produce a prediction. So if I want to understand of all the variables that are in rows, top we have wind, the V component, the U component, temperature, humidity, pressure, at different heights from the surface on the right to 500 or 5,000 meters up on the left. That's the whole atmospheric space in the matrix. And with the saliency maps, you can find out that the model's using this. And that blue blur is the temperature closest to the ground. So to predict temperature, it makes sense to use that. But if I look at rainfall, it turns out that to predict precipitation in the same point, it will consider humidity at the surface, which makes sense. But there's a very complex pattern there of zone wind and east wind, all the different components of the wind, which give rise to precipitation on that point. But if I move to Rome, the pattern of precipitation, of where it comes from, the ability of the model to predict rainfall has changed. It's not the same that was there for the Alps. And this, there are lots and lots of examples which tell us that these models will enable us to understand things happening in the physics and perhaps to discover new knowledge. And there's a whole set of new initiatives like hybridizing dynamic models and neuronal models. This is one case. The dynamic core, this one's called GCM neural, and the dynamic part is done with equations, and the parameter physical part is what the neural model learns. So this is a hybrid model. There's a part which is physics and another part which is neural. And this model works really well because, amongst the other things, it produces not just a deterministic forecast, but you can actually add noise. And with this noise, what you get is to simulate several plausible possibilities of future trends. So you're introducing a perturbation, not in the original conditions, but in the model, in a way that we've taught them to then respect what will happen with a certain probability. So these models are not just competing in accuracy of deterministic forecasts, but also in probabilistic forecasts. And what you have on top is the real path of a tropical storm predicted by the European model, and below the one predicted with this neural TFC in much, much quicker, and the outcome is, I would say, pretty similar. And so it's already available. There's diffusion models, there's a whole battery of models, and if I was given this presentation tomorrow, I'd probably come up with new examples. But to finish, where is the frontier of the use of AI in climate studies? Where haven't we reached yet to replace our standard models in the predictions of climate change in this final scale? And so in this final scale, there are, and what I'm trying to do is to predict climate change signals. And in that last scale, there are things that are being tried, starting with predictions for the global model to simulate that, to remove the model and use AI. But that's where the frontier is right now. So in conclusion, no one thought that this was going to happen 5 years ago. No one would have bet that this is where we would be today. Now the challenges are the climate forecast and prediction scales. That's where we're working in Cantabria. And hybrid models for climate are there to stay because, or for weather, because, for multiple reasons. Thank you very much. And I'm sorry that I've gone over my time, 2 minutes.
Bueno, muchas gracias también.
Right, thank you very much. That was another really interesting talk, which shows that we'll probably out of a job in the coming years, many of us. And now, moving to a bit of a more abstract topic, we have Professor Petros Koumoutsakos, who is professor in computational science and engineering and area chair in applied mathematics in the engineering school at Harvard. He's a naval engineer, mechanical engineer, PhD in aeronautics and applied mathematics from Caltech, has been in many different places, and most of his time he spent at ETH in Zurich, the Zurich Institute of Technology, where he was director of the Computational Sciences Department. He's a foreign member of the American Academy of Engineering, received the Gordon Bentley Computational Prize from the ACM, and his professional interests are the fundamentals and implications of computation and artificial intelligence for the prediction and optimization of flows in engineering, nanotechnology, and medicine. Especially interesting for today is what he's doing right now, although he's on a sabbatical. He's doing this sabbatical in this company, DeepMind, which Alfonso Valencia mentioned, which is that Google company that's doing AI development. So he's spending a year there now, I think. Whenever you're ready. Professor Koumoutsakos will be speaking in English, and you should all have headphones for the simultaneous translation if you need it.
Javier. Perfecto. Buenas tardes, señores y señores. Es un honor para mí participar en esta reunión. Estoy muy...
Good evening, ladies and gentlemen. It's a great honor for me to participate in this symposium. I'm very grateful to the Areces Foundation for the invitation. It's a great pleasure to present here in Madrid in front of this distinguished audience and colleagues, and most particularly in front of somebody who has inspired me for over 30 years, Professor Javier Jiménez Sendín. Javier is to blame for you having to put up with 20 minutes of my Greek accent in both Spanish and English.
Slides are in English, are in Spanish, but I will be speaking in English to smooth the transition. So what is the topic of my presentation is that humans, we are looking for knowledge. And as we are looking for knowledge, we have one new capability that helps us to acquire knowledge, and this is computation. And computation is important for the problems of understanding, of predicting, of designing, and in deciding. And I believe that, I wanted to also give a definition of what is Intelligencia Artificiale. So for me, Intelligencia Artificiale is the computational part of solving problems in the real world. The situation, if I move these observations in the sciences of physics and engineering, in the classical way of how we have been approaching physics and engineering was on the basis of mathematics. But at the same time, when we design aircraft and ships and other things, we had always heuristics. Today, we are having data, and we have also automated many of the heuristics. This is, in my opinion, the power of artificial intelligence. And I believe that the future will be the fusion of these two ways. I'm talking about algorithmic alloys that will cross and integrate different disciplines. And I believe that we owe to the new generations to not only tell them that machine learning will solve everything, but we need to cultivate their imagination and their thinking, because I think these are more important than ever. So since we're talking about thinking, and since I am Greek, allow me to go back, like all Greeks do, to where we were the best, perhaps, and that is 2,500 years ago. And this is the Academy of Plato. And Plato had a beautiful story, which I believe describes the pursuit for human knowledge. And this is the allegory of the cave. So according to the allegory of the cave, for those of you who don't know it, we are chained in front of a fire, and we don't see the real world, but the only thing that we see are shadows that are going in front of us. So we see only part of the world, and then we give it different names. We are saying this was a dog or this was a pet. And then what happens in the allegory of the cave, somehow one of us gets free and then goes out and sees the world and realizes that the world is three-dimensional and beautiful and has lights, and goes back, and because these are Greeks, he starts a fight about who's right, the shadows or the real world. So this is the pursuit that we have been having for many, many years. And we have been building amazing experimental devices to understand nature and the atom. And we have been also doing theory. And I would like to mention all these different names, and one particular name, which I think is probably the father of the modern computing, is Leibniz, who thought that when you have an argument, even between different philosophers, then what you will do is you will be able to quantify the argument the same way that you would have in two accountants. So computing, the beginning of computing, has unfortunately a very difficult story. This is von Neumann and Oppenheimer, and you know where the first computers existed. So they were designed to, they were first used to create atomic weapons.
The fourth atomic bomb has been successfully detonated.
And the story about computing is not the first time that someone talks about it.
And as all of you are, I'm concerned with the world in which we're going to live tomorrow. A world in which a new machine, the digital computer, may be of even greater importance than the atomic bomb.
And over the years, I had the fortune to play with different computers. This is my career in front of you. I had the opportunity to compute in all these different machines. And what has been amazing in these different machines, as one of the speakers earlier described about what is going on in the Barcelona Supercomputing Center, this is one of the, perhaps the only machine that I know that has magnified its capabilities by 1 trillion times. Imagine that you have a microscope or a telescope that you can do things like that. This is the fortune that we have today. So what I have been doing in my work is I have been trying to simulate different flows in the nanoscale. This is the flow of water inside carbon nanotubes. I have been trying to simulate flows of blood inside microfluidic devices because we were interested in identifying cancer cells. And I have been doing macroscale fluid mechanics, like the simulations of sock bubble interactions that you see here. Obviously, I'm not the only one who's doing things like that. There is also beautiful work that is happening in Spain. So here is one of the simulations of Javier. He's simulating the flow in a channel, and what you see is the flow, the velocity field in the near wall region of the channel. Now, to put this into some kind of a dimension, imagine that you're trying to simulate the flow over the wing of an airplane. I think that the flow that you just showed in the previous slide is basically the flow just above my nail, and that's about it. And if we try to simulate the flow in the whole airplane, we need to come up with numerical methods and clever ways and so on, and that is very difficult. And that is very difficult, especially when we try to forecast complex systems like climate, wildfires, and turbulence, where there are different scales. And then we have chaotic dynamics. These are expensive and to simulate and challenging to forecast, as the previous speaker said. So we spend time trying to think, how can I devise methods that I can forecast such type of problems? And there are methods. There are methods that we are using, but all these different methods, they have had and they still have limitations. So first time I actually interacted with Javier was at the Center of Turbulence Research at Stanford University. I was a postdoc at the time, and as a postdoc, you could do a lot of things, like take a course in computational psychology and other crazy things, and I did that. And one of the courses that I took was with John McCarthy, who is one of the pioneers of artificial intelligence. And actually, this is where my definition is coming, which is the computational part of the ability to achieve goals in the real world. And every single one of these words is very, very important in my understanding of artificial intelligence. So what I tried to do is I tried to compete against methods that people had at the time about simplifying flows. So if you have an original flow field, maybe you want to use fewer degrees of freedom to simplify it, and that's the so-called proper orthogonal decomposition. And then I found that you could actually, not me, but others, but I applied it to turbulence, that you could actually replace the proper orthogonal decomposition with neural networks, with linear activation functions. And eventually, when you just take this architecture and you make it nonlinear, you get actually neural networks. And I think as we were playing there, probably this is the first application of deep neural nets for physics. Now, I want you to appreciate these two papers that you see here. They're both talking about machine learning in fluid mechanics. The first one was done in 1999. Nobody wanted to publish it, and Parviz Moin was kind enough to allow me to publish it in the CTR proceedings. The other one has thousands of citations, but I want you to appreciate that when we started doing machine learning back in 1995, in the best supercomputer, these are the flops that you see on the left, what today takes about 1 minute or 2 minutes, back then it would have taken a year. And that made you think differently, and today we have the capability to think differently because of these computational capabilities. Obviously, I'm not so famous, so deep learning did not become so famous because of me, but because of this ImageNet that appeared a few years later by Alex Krzyzewski, Ilya Sutskever, and Geoffrey Hinton, where they were able to show for the first time that machine learning was able to identify images. And now, after that, what can happen is that once you're able to identify images, then you can make statements like this. How do you go about solving hard problems where you use lots of training data and a big, deep neural network, and success is the only possible outcome? Do you know who said that? You should. It's a very famous person. This is Ilya Sutskever, who is the co-founder of OpenAI and ChatGPT. And obviously, there were a lot of successes with this kind of thinking, but not everything can be solved only with machine learning. So I would like to show you some parts of my research, because machine learning is pretty good at detecting patterns in space, but at the same time, patterns can also exist in dynamics. Remember the allegory of the cave, that maybe there is some kind of underlying structure, there are some kind of shadows that we are trying to actually observe, and we don't need to know the whole picture of something. Or the other way around, imagine that we are observing shadows and we want to see what is the real world. But if the shadows are moving and there are sequences that are depending on physics, this is a challenge for machine learning. And in fact, time is a frontier for machine learning. So I want to show you how you can use machine learning to simulate physical systems. Well, you can take data that are coming from a physical simulation, and you can use them to train your machine learning model, and then you can ask your machine learning model, please predict. The nice thing about that is that you have the equations that also predict this data, and it's the equations that produce the data, so you can check how far in the future can the machine learning replace the physical simulations. Of course, you have to understand that for whatever predictions the machine learning does, it's about 100 or even 1,000 or even more times faster than solving the equations. And that is the power of machine learning. But then let's see how far can machine learning go. So this is some results from a particular equation, and you see how this unknown quantity, there is a partial differential equation that I skipped here, but you see how this quantity is evolving in space and in time. So I take some parts of these equations and I use it as data, and I train my machine learning models, and please take my word that this is a state-of-the-art machine learning model that I'm using here. And I want you to observe this red line as it goes up. It shows you, and on the right you see the difference between the truth, which is the full solved equation, and what machine learning does. So you see that machine learning is actually pretty good at solving things up to a certain time, and again, at a fraction of the cost of what the equation will be using, but at some point it starts to fail. It starts to fail, but it's interesting that at least on this particular method, it doesn't fail catastrophically, and in fact, if you observe what happens in the phase space, where you're observing a relationship between the first and the second derivative of the unknown quantity, you see that you will observe that even when the individual points are failing, if it happens that the latent dynamics, the dominant dynamics of the system happen to be in a well-preserved manifold, then machine learning can have a great chance. So here you see on the top it's failing, but still, it has not gone out of the manifold, so this is actually an interesting situation. This, as the previous speaker, Alfonso said, has been taken further, and is being taken further, and this is from the colleagues of the GraphCast. I'm part of this team at the moment, and I'm extremely impressed at how well, by data, they can do challenging things that equations alone would not have been able to discover, and this is for important things like weather. Now, there is another thing that is happening right now. So I would like to revisit the concept of things like turbulence. Can we now use machine learning to do turbulence? And what is the question that we have to ask for that? So I would like to show you one more algorithm to see about the thinking, not the details of the algorithm. So I would like to show you how you can use generative AI together with learning of effective dynamics to forecast complex systems. The diagram here is quite loaded. Let me try to explain. Up here, you have an expensive simulation. Let's say you have one of the turbulent flow simulations of Javier or one of my shock bubble interactions. So you cannot afford to run it for a long time, but what you can do is you can use machine learning to project it down to a lower dimensional space, to a lower dimensional manifold. And then once you have it there, you can use machine learning techniques like transformers to try to forecast what happens in these abstract dynamics that we don't really know what they really are, but we can use transformers to forecast them. And eventually, these things, as I showed you, will be inaccurate, but then we have trained a decoder, we go back out, and we iterate between the full dynamics and the latent dynamics. This is what I call led learning of effective dynamics. This is idea zero. There's lots of papers about that we have published. There is another idea that recently we have used, and this other idea is coming from diffusion models for images. The way to understand an image is to understand it as a sample from a probability distribution. We are a sample from a probability distribution of crowds. And once you decide that an image is a sample from a probability distribution, if you sample this probability distribution again, maybe you can get another image, or you can try to ask questions by using large language models of how you can take an astronaut on top of a horse somewhere in space. So this idea of the diffusion models is something that is very powerful for images. And now you can do also diffusion for time sequences. The same way that an image is the result of a probability distribution, you can imagine that every movie you watch, there is a probability distribution of similar movies, and if you sample them again, you can create new movies that they have some kind of certain characteristics. So we take these things, and now we take the simulations that we have, and instead of training to observe only static amounts of data, we are now observing batches of data. We are trying to take ideas from what these people do in computer graphics to try to make these artificial movies, and we try to take these ideas from artificial movies to do physics. So I would like to show this to Javier and everybody else, and there is this method called large eddy simulations where we're doing the same simulation in a channel. Unfortunately, we don't show it as beautifully as Javier teams have done, but this is a simulation that uses a certain grid points. And now if you take these diffusion models that I'm just describing, you can almost see that you can get almost one-to-one descriptions of the flow, except that now we are using a much lower dimensionality. You're about 50 times smaller than the large eddy simulations. And if you actually take into account, exclude actually, that you have spent time training, the thing on the bottom is about 1,000 times faster than the thing on the top. And this is, again, I guess only for Javier and others that they do fluid mechanics. We are not only able to capture movies and images, we are also able to capture with these generative models fluctuations, which is a tough diagnostic. And we can compare what these simulations are giving and what actually, how you can compare them with respect to what LES will be giving. Now, at the same time, there is another flow, which is a flow I did in my PhD. Imagine that you have a coin and you let it fall. This is a flow past an impulsively started cylinder. Who cares about that? Well, imagine that you have an airplane, and a cross-section of an airplane is a cylinder, and this airplane is moving up and down. Here, just this cross-section of the airplane is moving down. And depending on the speed that this thing is moving, it's producing these different patterns. So I would like to bet 25,000, 50,000, and 100,000 that in my lifetime, artificial intelligence will not be able to reproduce the detail and the accuracy and the insight that numerical methods have. This is actually the Reynolds number for the different flows. The symmetry was not imposed. It's an exhibition of how good the numerics are. And it was done like that because there are some amazing students that they know numerical methods and they know how to write code that they can do that. And I'm really worried that this kind of people, we're losing them because all the young people these days, they like to be trained in machine learning. Nobody likes numerical methods. Nobody likes adaptive grids. But I think we need to curate this part of science because it's important. I'd like to go away from simulation and to tell you one thing that I found actually very powerful for artificial intelligence, and this is not necessarily to simulate, but to optimize. In our group, we have done applications of optimization that they go from real turbines to combustion chambers to all sorts of simulations. Real turbines means real turbines that we optimized, combustion chambers that we optimized. So I would like to show you what was actually my ERC grant. I was very interested on the question of fish schooling. And the question is, why do fish school, and what can we learn from that? Is it because their behavior tells them that they have to school because they can find mates, or they can find food, or they can be eaten better by others? Or is there an energetic benefit that we can use, perhaps, to design swarms of drones, swarms of aircraft, and even the arrangement of wind turbines? So to do this, I used a method called reinforcement learning. Reinforcement learning has a tradition in many different disciplines, in psychology, in dynamic programming, in control theory. I think the place where it started was at Harvard, and it started with these pigeon experiments.
The two pigeons are at either end of a small ping-pong table. One pigeon pecks the ball as it comes toward him and knocks it toward the other pigeon. Other pigeon pecks the ball back across the table.
So if a pigeon scores,
the other pigeon can eat, and if it goes the other way, the other pigeon
a door opens and the pigeon eats.
Game, pigeon
and this is, it can be for the other pigeon as well, and that's actually a real video. And the voice that you hear is from Burrus Skinner. And can you imagine why Burrus Skinner cared about training pigeons? So this is the time of the Cold War, and what people were thinking a lot were thinking about missiles. So what you do is you put a pigeon inside a missile, and you give it food whenever the pigeon pecks on a particular image of a country that you want to bomb. And then if the pigeon pecks when this missile is flying, then the missile goes down. There is a whole story you can read about that. So this is the genesis of reinforcement learning. But reinforcement learning was behind the algorithms that they won the game of Go. Is behind a lot of things in robotics. It is about controlling nuclear fission. This is something that DeepMind is doing. And it is actually one of the key algorithms for what everybody is talking about these days, DeepSeek. They do use reinforcement learning as one of the key ways that they're doing what they're doing. So what is reinforcement learning? Imagine yourself trying to ride the bicycle. You don't need to know all aerodynamics and everything. All you need to know is what you need to observe to stay on the road, and then to push the pedal and you receive a reward that you're staying on track. All these things, they can be formulated with agents, and these agents, they can have individual neural networks and develop a policy with which they act. So in my lab, we didn't have access to machines like fusion machines, but for me, this was actually one of the revelations that I was happy to observe in my life. So we were training fish to swim. So you have a fish down here, and this fish is going to swim as it likes. And we had another fish, and the order that we gave to this fish, please try to find a way to swim with less energy than this fish down here. And we automated the process of searching different things. And you can start to guess what it's going to do. Is it going to change the way it swims? Is it going to change the shape, whatever? And to us, it was really amazing when we saw that the fish on the top, which is the one that is using reinforcement learning, what it decides to do, it decides to dive into the wake of the other fish because there is energy there. And then if it finds the right way to swim inside these vortices, imagine the people who do these things in the peloton, in bicycles. This thing was able to find it and find beautiful fluid mechanics. Eventually, it stabilized in a certain way, and it had a beautiful ballet of swimming and reducing its energy by 30%. We took this, and actually we studied the algorithms, and then we found in 3 dimensions we could not do that many iterations. These things are expensive. We found how to do it with 2 fish in 3 dimensions, and we found other ways. For example, the fish on the upper case that are in front of it. So these are things that at least my fluid mechanics would have never given me the opportunity to discover. So what we are doing now, we're combining very large-scale simulations. These are 300 fish. 300 is a magic number for Greeks. So these 300 fish are swimming together. This is resolved with wavelet-adapted grids. It took place at the LUMI that was mentioned earlier. And you allow me a second to look at it because I've never seen it in such a big screen myself. So it's a combination of trying to apply machine learning and simulations in order to study fish schooling in sizes that was never before possible. This is my last slide. So I'd like to talk about the future. And the future is similar to the past because I think we will still think, we will still philosophize, but I think we have a new partner that we should find a way to use it and to advance our knowledge by interacting with it. Ευχαριστώ, and I'll be happy to take any questions later.
Well, thank you, Petros. It was a very nice talk. But we have to speak about that, Elias.
Sure.
Okay. Bueno, entonces ahora.
Good. Now we're going to start this break. We've got a 15-minute break until 1:45. at about 6:55. What time? 5:02. Yeah, in about 15 minutes we'll be back. Thank you.
You don't expect me to believe that. Bueno, pues bienvenidos otra vez.
Good, welcome once again. And we've got 2 talks more and the Q&A. And the next speaker is Carlos Delgado, who works at the Ciemat in Madrid, and he's going to talk about the impact of AI on particle physics and astroparticles, and the future of that. Professor Delgado studies instruments and analyses techniques in this field to understand the origins of all this and dark matter. He's worked at Geneva, at the CERN, and at the Ciemat in Madrid, developing issues within particle physics and astroparticle physics. And now he is involved, I think, for the time being, in a telescope that I found in La Palma in the Canary Islands, an immense thing with huge amount of mirrors. And he's working in that there. He's taken part in transfer and industrial production processes for telescopes. He's been at the University of Tokyo as a guest, as a lecturer and researcher, and he's involved in telescopes and space research. Carlos, when you're ready. Well, thank you very much. I hope that you're not too tired, but we've had a small break, so I hope I can transmit to you what I want to tell you. Have you got the remote control there? Good. I'm going to talk about the impact of AI and machine learning on particle and astroparticle physics. I'll tell you what this is first. Now, particle physics is more well known, is better known, especially the paradigm, which is instruments at the CERN and the most important discovery of recent times, the Higgs boson discovery, which closed a circle within fundamental particles and particle physics. Particle astrophysics is slightly different, although it uses very similar techniques. What we do is we observe space, the universe, from the Earth, and there are events that happen in the universe that accelerate particles beyond what you can do with previous methods. And we watch these particles from the Earth to see what the properties of the objects that accelerate them are, and use those particles to learn about particle physics. And the particles that come from these events are the neutrons, and they come directly from the source in the universe, and they give us a lot of first-hand information. Gamma rays, high-energy gamma rays, they're photons, but with energy that is many orders of magnitude higher than the energy of what we can see with the naked eye or usual traditional telescopes. These particles come in a straight line, more or less, but they interact on the way. They cannot come to us from very far away. So they're large distances, but not on a cosmic scale. And they cannot, when they're very, very far away, they cannot reach us. They get lost on the way. And then we have the loaded cosmic rays, photons, electrons, nuclei, ionized nuclei that arrive, but they come through the intergalactic magnetic fields, and therefore they're off course, and we don't know where they come from, really. And what we do is since 2015, we've got a new way of looking at the universe, which is gravitational waves, or gravity waves, which are originate in the same events, and they give us additional information. They come from very, very far away, but they can tell us the direction and the distance at which these objects are. And they give us information very accurate information about what's happening in these objects moments before the particles are accelerated. So all this we watch using instruments that are the particle physics instruments, more or less the same instruments placed on the Earth, on the ground, but instead of looking at particles generated within the device, we look towards the sky. And it allows us to access the highest energy phenomena in the universe, beyond anything that we can witness on Earth with a particle accelerator. What happens with the four fundamental forces? The only way to watch the action of gravity in high energy phenomena is with gravity waves. And also we can search for dark matter that permeates the universe. And these particles go through that matter, so we can get information about dark matter too. So this is a typical instrument that is used for particle astrophysics. It's like particle physics, but in a slightly different way. This is the telescope that was described, Cherenkov telescope. It's a huge mirror that points at the sky to see the interaction between photons in the atmosphere. And then we have neutron on the ground chamber. When a neutron enters here and interacts, we look at the results that derive from that interaction. This is a detector of loaded cosmic rays, very high energy, and there's a huge amount, there's like a grid of dots distributed in enormous surfaces, because the energy photons interact with the atmosphere and they produce like a cascade of particles, and you've got to infer what has arrived. And not many arrive, so you need giant areas, surface areas, 1 per square kilometer per year, for instance, so you need a huge amount of square kilometers. This is a cosmic ray instrument, lower energy, at the International Space Station, and it's an AMS, very similar to the detectors at the CERN. And this here is a gravity wave detector. This is the only one that is slightly different. It measures how the distance from this point to this, these are lines, photo multiplier lines in the Antarctic. This measures a few times more than the Eiffel Tower, to give you an idea in height. And it observes the interaction of neutrons with the medium, which is ice in this case, and it issues or emits Cherenkov light, it's called, and the detection allows us to infer the original direction of the particle of energy. This is just to give you an idea of all these different techniques and instruments, and this is what they have to do with particle physics. Now, I'm going to talk about what is the concept of AI that I'm going to apply to this talk. The idea is that there are many different techniques that are older. They go back to the 19th century, in fact, if we really look at it, that allow us to discriminate between phenomena based on characteristics that we observe in those phenomena. We have the linear models that go back to Fisher, and what they do basically is build a linear model to discriminate between things. Then we've got a Markov model, based on probabilities, that allows us to discriminate based on probability. And there are many other models. And basically, for many years, since the 90s, all these models that are linear, decision branches or forests or trees, decision trees, were the different events, depending on what box they fall into, they're organized in one way or another. All these models have been used in particle physics since the 90s with great success. And the kings of this field have been, or are, the processes based on decision trees, what we call random forests. a series of boxes that are brought together, and then trees which are based on a little box that you build. What falls into the box leads to another box and then another box. This has worked very well, and in particle astrophysics, at least, all results that have been obtained in the last 20 years have depended on this kind of model. In fact, at the Cherenkov telescope, the separation between signal, a lot of images arrive, and you want to see what is a gamma ray and what is a proton. The discrimination between those two things has only been possible using these techniques to discriminate protons from gamma rays with a 99% degree of efficiency, and protons are about, well, the gamma rays are about 1% less than the sample. So it's very, very strong, very powerful. What I'm going to consider AI in the rest of my talk is anything that hasn't been successful to date, hasn't been used so much. Deep rays or convolution networks. Now, to give you an idea of where we can use AI, I got to tell you about how the experiment works in particle astrophysics and physics, because depending on the place, these techniques are used differently, and it's important to identify pain points or areas where there might be issues. This is an example of a particle going through a detector in space, and the particle interacts with the instrument. There are signals, analog signals mostly, and then you have to decide, of all the things that have produced signals, are there any events that we should store and study? Because if you look at the sky with a telescope, for instance, the amount of data is huge, 10 to the power of 15 bytes per second. So, and to observe a source, I mean, that's a huge amount of information. When you look, you'd have to look at the sky for 100 hours to see anything. So one single object brings with it an unmanageable amount of information, so you have to break it down and keep little parts of it. So this is what is called a shot. And a shot is normally an electronic device that says, or system that says, this is interesting, let's process it and store it to study it at a later date. We got a shot, we process the signals of from the instrument, and then those signals have to be reconstructed. They're stored, and then we must decide what they mean physically. Particle came in this direction with this level of energy, with this mass, with this speed, with this load or charge. And this is done in a process called reconstruction, and then it's archived. But instruments are very sophisticated, and the interactions are very sophisticated. So to have an instrument that allows you to shoot, reconstruct, you can't do it just straightforwardly. So you've got to buy a replica, produce a replica of all these instruments, this in blue here, which is a simulation of all these instruments that allows you to understand, when you look at something that is processed, what its meaning is, so that you can do a reconstruction. You apply that reconstruction to your simulated data, and you look at, you compare one thing and the other after you've archived it to infer what kind of particles you've observed and what their characteristics are. Now, when you finish all that, the final step is all the particles are reconstructed. You've got to decide, this is noise, this is background, this comes from the source, this doesn't, and that is the analysis phase, subsequent analysis phase. So when you introduce AI, initially you could, what you've got to do is you've got to take all these data, the results of the simulation, and with that, you've got to do a better analysis or instrument. That's what we want to do. So really it's a learning process. You learn, you feed AI, whatever that means. It can be classic machine learning or deep learning. And then based on that, you wait. You expect to learn more and build new algorithms and these are the areas where things can be done that allow you to improve the shot. See things that you couldn't see before because you missed them when you shot, or improve the processing, eliminate noise, or improve the reconstruction. When you say the energy was such and such, you can be more accurate. Also, there's a frontier, so to speak, a border, which is the archiving. There's an enormous amount of information that you don't really have to manage. We're looking into how to build encoders that reduce the amount of information of the processes and the amount of information that has to be archived. And then the simulation has its issues. It takes a long time, as has been said, and that can be improved a lot using AI. There's another problem with simulation, which is that often these techniques are high precision techniques, but reality is perverse and it's not as fine as you would want it to be, or it's biased. So we're developing techniques to make simulations come closer to reality and reduce their bias, because you're using data based on initial hypotheses. Now, I'm going to tell you, so that you can see this, some examples. These represent a very small part of what is being done, but I think they'll illustrate what is happening in the field. This is just to give you a quick example. This is what a Cherenkov does. This is Cherenkov. This is a particle. Incoming particle into the atmosphere produces an electromagnetic cascade called an atmospheric shower. This emits Cherenkov light, which lasts for nanoseconds. That light is collected by the telescope and digitized in a camera, and little films are made. They're 14 nanoseconds each. And then each frame looks like this. It's an amount of light that arrives onto the camera, and that light arrives at a given point in time. Now, what we do here, we describe cinematic phases or stages, and then we use the random forests, the decision trees, to discriminate whether it's a charged particle or not and determine its energy and direction. That technique has been very successful, but we wanted to go beyond that into a new application of the Cherenkov telescope, whose aim is to look at the universe like we've never done before with gamma rays. And what the community is doing is it's employing deep neural networks, where instead of mathematically describing images, you give it the images directly. Now, they're not images, they're really little films. It's a bit more complicated, but the idea, using random forests, we take this as a reference of how much can be observed, which is here. Currently, what we see is that when we use deep neural networks, we can observe sources which are 6 to 8 times weaker. That increases the number of objects that we can observe at low energy levels, which is where that's the speciality of the Cherenkov telescopes. Now, this in itself is, when it's applied, because these Cherenkov telescopes are going through trial phases yet, this will mean that we could probably see parts of the universe that cannot be observed right now, because at lower energies we see many more sources. But here you see there are 2 areas that are different, 2 little curves that are different, and that's important, because what we see is that if our simulation that we use to train the neural networks differ slightly, however slightly from reality, we have very big variations to up to 20 and 30% of the performance. And we don't know how to reduce that. today at this time. So we've got limitations. They're complications. They're complicated because we've got to simulate the instrument, but also the atmosphere. And the atmosphere we measure very well. But there are phenomena that happen while we're observing that we cannot control. And you can't retrain the whole system constantly every time you observe. It would be too much. And that's one of the issues we've got to address. And I'll tell you about something we're doing about it in a minute. And this improves not just the amount of sources we observe, but the resolution and the energy. How well we get to know the energy of the particle, and also how well we know its direction. And this, because we can observe the universe, we can observe many more sources, and we can study them with a much greater detail. Another example where the application is being developed is with gravity waves. This is a very quick example. This is how we see the signal in the absence of gravity. This is time in seconds, and this is the amplitude of the movement that the detector sees. There's a lot of noise. There's a very silly example. The methods, classic methods to extract the signal would tell us there's nothing here. This is PCA, a very classic, very old technique, very easy to apply. And this is using a deep neural network that has been trained with the type of signs that you expect to observe. So there's no great difference here. But when a gravity wave or gravitational wave comes in, this is a very strong one. The noise is tremendous. You can't see much. But with a PCA technique, classic technique, we can't see the signal very well. The original sign is in yellow and the blue is the reconstruction. So the properties that you infer. But using DNN, the reconstruction is perfect, as you can see on the right. And this is simulation, not real.
Ahora mismo hay una cantidad ingente de grupos estudiando cómo hacer esto bien. Bueno, y ahora quería ir rápidamente sobre lo que os decía, ¿no? De que nuestro principal problema es que las simulaciones pueden ser no lo suficientemente cercanas a la realidad, por la razón que sea. Pues esto hay un grupo de gente que está trabajando en técnicas para aliviar este problema. Esto simplemente os voy a poner un ejemplo muy rápido, que es nuevamente basado solo en simulaciones. Esto es una simulación de un detector de rayos cósmicos de muy alta energía, como puse antes, es un rayo cósmico choca la atmósfera, produce una cascada y observas la señal en función del tiempo en un montón de detectores colocados en el suelo. Entonces uno entrena una red neuronal con esos datos de la simulación y ve que bien eres capaz de reconstruir lo que has introducido. Eso es lo que se ve aquí. Aquí es simplemente la energía real de la simulación, porque la conoces de la simulación, respecto a la energía que reconstruyes con una red neuronal, que es muy bueno, o sea, reconstruye esencialmente lo mismo. Por eso es una línea que dependiente uno, o sea, reconstruye lo mismo que metes, esencialmente. Tienes una resolución muy buena de un hexaelectronvoltio, que es muy bueno para estas escalas. Sin embargo, si uno introduce un pequeño ruido en los datos que quiere reconstruir, en este caso simplemente cambiar la cantidad de muones que produces, que eso es un parámetro que ajustas en los modelos de interacción en la atmósfera, pues observas que se desvía muchísimo. De hecho, tiene una resolución 8 veces peor. Y esto es el principal problema que tenemos en nuestro campo. El depender tanto de las simulaciones y que pequeñas variaciones en las simulaciones te introducen grandes problemas en los resultados que obtienes con redes neuronales. Sin embargo, estos señores, que son de la Universidad de Aachen, hicieron un proyecto muy interesante, que es usar redes adversarial networks. Son redes neuronales que compiten entre sí. Entonces, lo que tenían es, se cogen el Monte Carlo, que es como llamamos a nuestras simulaciones, son simulaciones Monte Carlo, y se cogen los datos, un conjunto de datos, al azar, típicos de lo que está observando. Entonces, tienen una red neuronal que lo que intenta es mejorar, o sea, hacer que el Monte Carlo se parezca lo más posible a los datos. Y tienes otra segunda red neuronal que intenta diferenciar lo máximo posible la simulación de los datos. Y lo que haces es que las dos vayan compitiendo, las dos redes neuronales vayan compitiendo y que intenten ganar ambas. Cuando haces eso, lo que ocurre es que esta de aquí intenta acercarse lo máximo posible a la distribución de los datos, de tal manera que ésta no sea capaz de distinguirlos. Y eso, si se hace inteligentemente, con cuidado, se puede hacer sin que destruyas la calidad de tus simulaciones. Esto es lo que se observa aquí. En los datos, la simulación son los puntitos, los datos reales sería la línea, y el rojo es la línea pasada por esta red neuronal que la convierte en los puntitos. O sea, realmente está por encima. Este es hacia donde va la comunidad intentando resolver este problema. Rápidamente os enseño qué tal funciona. O sea, simplemente de lo que estábamos antes, que era una gran diferencia, pasa a una mejora 4 veces mejor que lo que obteníamos inicialmente. Hay una gran parte de la comunidad que está trabajando en resolver este problema. Simplemente voy muy rápidamente sobre otro sitio donde se puede aplicar ese tipo de cosas, que es bastante interesante y además mezcla dos palabras interesantes, que es Machine Learning y Quantum Computing, que es el uso de técnicas de árboles tensoriales, que es una técnica de computación cuántica, para hacer Machine Learning en dispositivos integrados. En este caso, estos señores de la Universidad de Padova, de una empresa de mecánica de Quantum Computers, lo que hacen es que introducen en una FPGA, que es un dispositivo que uno puede comprar, son capaces de introducir un sistema de disparo con inteligencia artificial que reacciona en tiempos del orden de microsegundos, fracciones de microsegundos, con lo cual es capaz de introducirse en los sistemas de disparo. Voy muy rápidamente a mi penúltima transparencia, digamos, que es ¿cuáles son los éxitos de casos rotundos? Pues mira, he preguntado a ChatGPT y me dice que no hay. Realmente en física de partículas, y astrofísica de partículas, no hay casos donde no se haya podido hacer algo porque no haya inteligencia artificial. La razón es que es relativamente nuevo, somos muy conservadores y que no somos capaces de explicar por qué las máquinas hacen lo que hacen, las redes neuronales. Y en física de partículas es fundamental entender por qué ocurren las selecciones. Esto es un problema que hay que resolver, y hay grupos intentando resolverlo, pero paso por ellos y les dejo que esencialmente es el gran problema que tenemos que enfrentar.
Bueno.
Okay, thank you very much. And now we have the final talk on, well, the final talk as such. We will have some time for the Q&A after. And this next talk is going to be a bit different from the previous ones. The previous ones were about the application of AI to a certain field. And this next one, if we look at the title, talks about the mutual impact between AI and something, which is the brain. Because our next speaker is a neurobiologist and works in brain research. And he spent his whole career on studying the brain and things which are not just interesting, but also useful mechanisms involved in depression and anxiety. So clear medical applications there. He is chair of many things, chair of the European Research Network on the Brain, the Spanish Neuroscience Society, the Confederation of Scientific Societies of Spain, and amongst other things, he is a member of the Academy of Science of Spain. So you have the floor.
Ahí estamos, muchas gracias. Muchas gracias por la introducción.
There we go. Thank you very much for that introduction. Thank you very much for the invitation. I hope you're not too tired. Biologists or specialists in biomedicine know that the main factor in loss of attention is tiredness. And that's why it might be a good idea to have the drinks before we started the talks. Without needing to use AI, I've been able to draw that conclusion quite clearly. But anyway, as Javier was saying, the relationship between AI and brain is a symbiotic relationship in the sense that the structure of the brain, the way in which neural nets are structured, or how learning happens, and synaptic plasticity, which is the changing the efficacy of synapses in the brain, have driven a lot of the developments in AI, which is an interesting name, but not that accurate. I'd like to define two things. First, artificial intelligence maybe is something you should only apply to those neural nets, which shouldn't be called neural nets. They're node nets, not neurons, because I'd like to show you that a neuron's a lot more complex than a node in a net. But these deep learning nets, I don't know why it's deep learning either, but it is learning, and in that sense, we might probably be talking about intelligence, but also the development of these algorithms which are related to AI are making it possible to understand how the brain works as well. Because the brain is extremely complex and we need these kinds of tools to understand how it works. And they are enabling the modeling and simulation of the brain and data analytics in neuroscience. There's huge quantity of data, genomic data, but also electrophysiology data, which are extremely important and which are relevant to our understanding of the nervous system and how it operates. And that is quickly improving how brain-machine interfaces are developing, how brain waves may be interpreted as input to the machines, and how the machines may even predict what you want to do simply by thinking about it through monitoring brain activity. And that clearly is also bringing about diagnosis of brain diseases, well, not just brain diseases, all kinds of diseases, because it's a horizontal effect. Early diagnosis, but also the development of completely personalized treatments when using these kinds of algorithms and predictions. But let me start with the history of this whole field, because if we look back at the milestones that have fed the evolution of neuroscience, clearly you have to start with Cajal's neuronal theory, the end of the 19th century, beginning of the 20th, and I dare to say that comparable to the significance of these milestones, we have what has been called the development of artificial intelligence, the development of algorithms, and we are in that milestone, in that phase, which is a fundamental fact in order to understand the brain. Just as important as the discovery of synapses, hypothesized by Cajal in his neuronal theory, in which Ed Sherrington described and even gave them the name and characterized them, and that's why he got the Nobel Prize. I forget which year exactly, but I think it was like in 1936 or so. And the whole discovery of the biochemical mechanisms, the discovery of neurotransmitters like dopamine and serotonin and glutamate, Langley, Dale, and Otto Levi, who were crucial in this understanding of brain neurochemistry. Dale was a student of Langley's, and Otto Levi and Dale received the Nobel Prize also in the first half of the 20th century. And of course, I need to mention, and probably if you make a list of milestones in neuroscience, they will be exactly the same ones. But of course, it's always open to discussion. But I just wanted to mention the Hodgkin and Huxley model. They also got the Nobel Prize in 1963, I think it was. And that, for a model which is, dare to say, one of the first models that used artificial intelligence in the first half of the century, in that context of the first half of the 20th century, because what they did was to measure efficiently the dynamics of the changes in membrane permeability to sodium and potassium, and with that to come up with equations which we might call algorithms today, which enable them to predict the shape and the generation of the action potential. And they did this in the giant squid, but in the giant axon of the squid, but it would apply because all of these things have been preserved throughout evolution. But that model was able to predict not just the shape, but also the conduction of the activation potential through along an axon, and that's probably why I'm saying it was the first example of the use of artificial intelligence. And one of the things it predicted was that there would have to be ion channels in the membrane that could open quickly and allow the flow of ions in and out, of ions in and out. Something that was not proven until Berghem and Chapman, who also got the Nobel Prize in 1973, I think it was, developed what is called the patch clamp technique, which is not really very easy to translate, because the patch clamp model was possible because of the models they made. Well, the Hodgkin and Huxley model was enabled by what these measurements they did with the patch clamp technique. But of course, there was the whole technology revolution of neuroimaging with MRI and high-resolution microscopes and all the cell imaging techniques that were developed throughout the 20th century. And of course, we also should mention the concept of neuroplasticity, which Cajal hinted at with no evidence, but he was quite a visionary, and he wrote it down. And it wasn't until Ronald Hare and a few others, Ronald Hare's been mentioned here already, and Tim Lees, Jerry Candell, were the main heroes in the study of neuroplasticity or synaptic plasticity of the brain. Only Eric Kandel got the Nobel Prize. And then in the 21st century, of course, there's the development of molecular tools which have enabled us to modify genes and check their function and stimulate neurons with light, which is optogenetics. Oh, and finally, of course, there's the frontier projects that are currently underway, which are trying to understand the connectivity of each neuron in the brain, not the human brain. The human brain is still too complex, but in simpler brains like the mouse, or, as I will show you, the fruit fly, Drosophila, which are certainly driven in part by the development and the appearance of AI. And I wanted to show you that the way in which the brain is structured, the neural nets, well, artificial nets and artificial intelligence have been inspired by the way the brain is structured. And we have these wonderful drawings by Cajal. And the one on the left here is the reptilian brain cortex. They say artificial intelligence is based in the human brain, but it's not true. It's based on the brains probably of the connectome and the structure of the human brain. We know a lot less than we do about lower species. But there's a basic principle here, which Cajal already evidenced with these arrows, and that is that information flows through these fibers that are connected with the various neurons, and these neurons emit an axon through which the information flows. Part of that structure is already processed. And if we go to this other drawing, which is also amazing, that's of the brainstem, and here you can see the Purkinje cells, which we're looking at them from the side here, and these Purkinje cells have two main inputs: these fibers that are called climene fibers that produce synaptic connections with about 2/3 of dendrites, and these fibers from these grains, which are called parallel fibers for obvious reasons. And these cells also receive inputs that are represented here by these interneuron, which are inhibitory, they're not excitatory, and essentially that's machinery that can learn motor behaviors. And so clearly this will remind you a lot of what you've heard here about these deep learning neural nets. that are able to learn. But I wanted to show you that it's not easy for the following reasons. If you observe how AI experts draw their neural nets, actually what they're doing is to build nodes, nets made up of nodes, and the nodes have various inputs, certain weights, and these weights are integrated there with a function which could be a sigmoid or of whatever type, and it produces an output. This is very similar to how neurons work, but it's a bit simpler. And these elements, these nodes, are grouped into nets, which are activated in order to provide a single answer. If we look at another Cajal drawing, this is very well portrayed here. This is the hippocampus. I think it's the hippocampus of a rabbit. And you can see here how these fibers that come from the cortex connect with these granular neurons of the dentate fascia. Layer, as it's called, with axons which form these Schaffer lateral branches which connect with these neurons of layer C1, which is the main output from the hippocampus. This is not entirely true. This is probably one of the very few mistakes Cajal made, but it's still valid. But the thing is that this structure, this circuit, is very reminiscent of this neural net here. It could be the dentate fascia connected with the CA3 cells, the CA3 cells connected to the CA1 cells, and you get the output of all of that information through here. But I said that those nodes are very simple, because if you look at how a neuron, a pyramidal neuron in the C1 layer lights up, you can see that it has a huge number of branches, all of which are receiving inputs, which in this model are, we only see 3, but this is actually hundreds, thousands of synaptic connection links. And this is not just, and it's not the same if it's in the apical dendrite or in the basal dendrite. And if we look at these dentate fascia cells, here, what we can see, and I'm going to amplify this a little, you can see that it's full of these small branches, or spines, dendritic spines as they're called, and each of them has input from other neurons. And in the Purkinje cell, for example, which I mentioned earlier, it was estimated that there's 100,000 synaptic connections. So the magnitude of the problem, the degrees of freedom which this biological system the brain has, will put any neural net, no matter how complex, in the shade. But clearly progress will be made here, and when we are able to simulate maybe 10% of the complexity of a structure like the hippocampus, we will have gotten very far indeed. Another important thing I wanted to mention here is information about a synapse, which is not just a simple structure. These are Purkinje cells. It's something we've published recently in our lab. And each of these lights there represents a synapse connection, where you can see there are neurotransmitters connected with vesicles that release cell signaling and activate various postsynaptic receptors, which can take the information from the presynaptic cell and activate the postsynaptic cell. And there's 700 or 800 proteins that are working in coordination in thousands of a second. And so the biological problem required to understand this system is huge. And if, with the patch clamp technique, we were to obtain a record of one of these cells, this is not exactly a Purkinje cell, but it doesn't matter, it's a hippocampus cell in the lab. You can see that each of these responses with multiple amplitudes corresponds to the activation of 1 or 2 synapses in this cell. And so the way in which a cell works is quite different in terms of complexity than a neural net, deep learning. And another thing I'd like to share so you can see the problem with the issue of plasticity, still wonderful drawing by Cajal, and you can see the frontal view of the same cell with the climbing fibers and the parallel fibers, cross-section here, and there's the diagram. And if you stimulate this fiber, or activate this fiber, this climbing fiber, you get this response, climbing fiber. But if you apply a second stimulus, the response to the second stimulus is not the same. Something which I don't think would happen in a machine learning neural net, whether that's simulated or not. You get half the amplitude of the response here, and if we applied a third stimulus, it would also be smaller, all the way to the axis. And so the synapse remembers whether there's been a prior stimulus, and it will change its response based on that. And if we do the same thing, but instead of stimulating the climbing fiber, we stimulate the parallel fiber, it turns out that the second response is double the first. So this synaptic memory of the same cell in two different synapse systems will be very different. And another important thing is that the weight that this synapse has is a lot greater than this one, because notice the calibration scale is like 10 times greater. So that's what is called synaptic short-term plasticity. There's also the long-term plasticity. And what long-term plasticity does is that under normal condition, if this is the release of the neurotransmitter and the activation of postsynaptic receptors, when there's an enhancement of the synaptic strength in a way in which I will demonstrate in a minute, there's increased release by the presynaptic cell of these neurotransmitters and an increase in the activation of the receptors that are sensing that neurotransmitter in the postsynaptic cell. And you can see this in these graphs. This is the amplitude of the response, 100%. You evoke rapid stimulation trains with an increase, a transient increase in the synaptic response, and then this potentiation, which is what's called long-term potentiation, which remains. And the difference between these dots, which are gray, and the red and blue ones, is that this, which obviously shows less ability to enhance the response after the same stimulus, is because this was done in a mice model with a Down syndrome. And so there's a deficit in the long-term plasticity. And another change in synaptic efficacy is LFS, which is what happens when the stimulation happens. Instead of with high-frequency trains, you stimulate for a few minutes with low-frequency trains, and that causes a drop which lasts partly. And in the Down syndrome model, this doesn't happen either. So that gives you an idea of the number of degrees of freedom in synaptic connections in brains. And perhaps artificial intelligence might be able to mimic this someday with perfected algorithms, but right now it is quite far from that level of complexity. And in success cases for AI use, or how AI is contributing to help neuroscience understand how the brain works, I wanted to show you a couple of examples. These are fruit flies in their larval phase, pupal, juvenile, and adult phases. And back in 2003, 2 years ago, this was published, a team was able to analyze the connectome of the fruit fly larva, which has quite a simple brain. This is basically a stick. They say it has a brain, but in any case, they were able to detect and analyze 3,000 neurons connected by over 500,000 synapses. And here's the chart showing how presynaptic neurons connect with postsynaptic neurons and the degree of connectivity. And this was possible thanks to the availability of algorithms to analyze this type of data. But last year, at the end of last year, there was another publication, and that is the whole brain of the adult Drosophila or fruit fly. And you may not be able to see this, but every one of these dots is a neuron, and this was done by using AI algorithms running anatomical data, which had been published 5 or 6 years earlier in Cell, with cross-sections of the fruit fly brain, which were analyzed in full. And this was done by a consortium, Flywire, which includes 127 institutions from all over the world with, I would say, thousands of researchers. And in fact, they used experts who were not entirely connected to curate the data so they would be reliable. And with that, they were able to reproduce these types of diagrams where each cell, which has a name, is connected to another cell, uses a certain type of neurotransmitters, excitatory, inhibitory. Of course, they don't know what the weighting is, and that's a problem, but at least we have this kind of circuit diagram which is enabling us to run experiments of computational neurobiology and obtain predictions which couldn't be done with biological experiments. And I mention this because some years before, they had also solved the connectome of half the brain of the fruit fly. And that took 70, well, a way of measuring the effort required, 70 people a year. That is, 70 people working for a whole year, or one person working for 70. And half a fruit fly brain. And to solve the whole brain, thanks to the improvement in AI algorithms and their ability to interpret images, that was reduced to a half, 33 people a year. And that, I'm sure, will be optimized more and more as the algorithms are improved. And I have a couple of examples. I hope to finish on time. I think I will. And that is, how is AI impacting the development of neuroscience? I'm sure you'll be thinking about whether these machines will be able to read our minds and so on. But I'm not thinking along those lines, which are more to do with science fiction. I think this example has been mentioned by Alfonso Valencia already. But with these machine learning technologies, or machine-guided design technologies, or however you want to call them, you can design more specific regulatory elements. These are sequences that regulate gene expression and make a cell differentiate into an astrocyte or a neuron or a microglia cell. And so they're now trying to improve the gene therapy to the kind of specificity of neuron subpopulations. This can, of course, be used in the brain. It can also be used in other nerve cells. And the next example I have, which is more connected with the topic of mind,
Utilizando también
is that using AI algorithms and deep learning, you can train based on brain waves registered with electrodes, surface electrodes that are not invasive. You can train word synthesizers in such a way that somebody who cannot speak can speak. The machine can speak by looking at the brain waves of the person, and this is done with systems that improve the spectra, and the narrative becomes quite positive. The AlphaFold system, which Alfonso Valencia has mentioned, is spectacular. Half of the Nobel Prize was given to David Baker for this, and the other two were the Google DeepMind people. And to determine the atomic structure, like we can do now with AlphaFold, It used to be a tremendous headache, very costly, years of work. You had to have the protein in adequate concentration, clean enough. You had to crystallize it, had to crystallize well. You had to have rays of beams of light, proper diffraction. That was years of work. Now, based, as Alfonso said, on the linear amino acid sequence, you can predict the interactions in secondary, tertiary structures, and finally in quaternary structures, and you can even invent proteins that don't exist if it were necessary. So in I've got 8 seconds left. This is, in a word, a summary to focus the problem. AI is based on circuit organization, synapses, and the key concepts are that in a synapses, an electric signal or chemical signal is transmitted to another cell. This is represented in the artificial neural networks and with weights. Very similar. The synapses can change its efficacy. The neural network is modulated by changing the weighting, and like the brain processes hierarchically, processes things we don't see with our eyes, we see with our brain. And the light that enters our eyes and activates a fantastic computing system which is in the retina, it organizes itself in layers in the eye and then in the cortex of the brain, and that allows us to see, well, it's similar. What happens with deep learning is similar, but there are some significant differences that I'd like to highlight, and I've said extreme simplification, and the synapses are chemical, electric, they're inhibiting, and the more complex systems of AI mimic this not so well. And then there's the scale. Human brain has 80 billion neurons, billions of synapses, and no AI network has approached this. The biological synapses work in function in real time, whereas artificial models train using discrete data sets. And then sustainability, a brain, in spite of the fact that it is the organ that consumes the highest amount of energy in the body, what it consumes is what a light bulb consumes. Most of that energy goes into preserving or maintaining synaptic energy. But in a report from the Academy of Sciences of last year, it is said that to train ChatGPT-3 once, just a single time, consumes 1,287 megawatts an hour. And that's what it needs in energy, in power. That's what a nuclear power station needs for an hour. The question is that sustainable or not? And with that question, I'm going to leave it, and thank you very much for your attention.